Hi guys, welcome to another one of my lectures, and today I'll be focusing specifically on the basic foundation of electromagnetism. Now, like the name suggests, we are looking at the effect of a magnetic field which is due to a current. So the first thing we are going to establish based on my last video is that there are magnetic fields which exist around any current carrying conductor. So if it were a long straight wire or a solenoid or a flat coil, what you would have noticed was that there would be a generated magnetic field. Now, electromagnetism deals with the question, what happens if a conductor with a current is placed perpendicular to a magnetic field? So the question begs to ask, what happens now if I take a typical wire carrying a current into the plane, right? And as we saw in the last video, based on the right-hand grip rule or even the right-hand Maxwell screw rule, you will be able to determine that the direction of this magnetic field is like this. So what happens now if I wanted to insert an external magnetic field? Because remember, this takes the wire into the board, so it will be perpendicular because to my external magnetic field, because here my magnetic field lines will extend north to south, out of the north into the south. The reality is there will be an interaction of field lines. So if I were to enlarge on this diagram here, you will see that I have field lines which go north to south, right? And that's your basic uniform magnetic field. Now, what happens if I have a wire carrying the current into the page? And that, of course, the wire is perpendicular to the field. Now, here, I can draw my magnetic field pattern around that wire. And it will show me that at points, you will have here, at the top, the field lines will follow each other. But we have an issue. At the bottom here, the field lines cancel each other because the green field lines will go in an opposite direction to the blue. Where the field lines cancel each other will cause a resultant force to be directed. So basically, if you take a wire carrying a current, once there is a current, there's a magnetic field. If I take that magnetic field and I insert it perpendicular to the magnetic fields of an external bar magnet, then there becomes an interaction between that external magnetic field and the magnetic field around the wire carrying the current. The interaction of those two fields would result in a force. Why? Because each field is a force field. So when those two force fields merge or combine, it produces a resultant force. Now the challenge becomes, how do you determine the direction in which this force is acting? Now the direction of the force, you can manually draw out each field, and where the fields cancel is where the force is directed. Or you could use a rule which is called Fleming's left-hand rule. So the rule basically uses the first three fingers of your left hand. So you would have here your thumb, right? And that represents the direction of the force. Your first finger, which would represent your field. And of course, your second finger, which would represent the current. So here you would have the three fingers being mutually perpendicular to each other. And when you use them, in this case, your middle finger, which is your second finger, will go into the page. Your index finger goes from north to south, so that causes your hand to give your thumb pointing downwards. So you are merging the three fingers in your left hand. You are making sure that they are perpendicular to each other, and if you use them and you manipulate that, you will get the direction of the force going down. Now, how is this useful? Some of the main applications of this force, you can look at the operation of a loudspeaker. You can look at the operation of a DC or even an AC motor, right? And I have found that these two are the main uses of this force generated. So if we consider a loudspeaker is a device where you convert electrical energy to mechanical energy, because you are looking at the vibration of that device. So it in essence consists of a magnet, and you can have a north pole between two south poles or a south pole between two north poles. Around the center of this wire, I wrap a coil of wire. Center of the magnet, I wrap a coil of wire, and I connect it to an AC source. Now, connected to the magnet, we normally attach something called a paper cone. And in essence, what happens is that as you have your current flowing here, you would have your magnetic field generated around the wire, and that interacts with the magnetic fields around the magnet. So in essence, you will have your force being produced, and this is your paper cone. So as the force produced changes direction due to the current being alternating and changing position, you will find that that change in direction of the force is what exerts a force on the paper cone. And the paper cone will begin to move back and forth, back and forth, back and forth. And when the paper cone begins to vibrate, it sets up a sound wave in the surrounding air. And when that happens, you will be able to hear the sound produced. Okay? Now, if we consider an electric motor, we are going to consider one which uses a DC source. All right? So your basic electric motor would obviously have your magnet. We are going to insert a split ring commutator, which is just a C-shaped ring, and we're going to connect it to our rectangular coil. I then am going to rest carbon brushes, and I connect these carbon brushes to a battery. So the purpose of the split ring commutator is that it's C-shaped, and if it were AC, I would use an entire ring, a whole ring, which is called a slip ring. But if it's DC, you use C-shaped rings, which is why you call it a split ring DC. And if it's AC, you use a whole ring, which is a slip ring. Now, the purpose of them is that they rotate with the coil and they rest against the carbon brushes, which electrically connects your coil to your source. All right. So based on my conventional current flow, my current flows in this direction. Now, if we use Fleming's left-hand rule, at this point, it would look as if the current is going into the page, and here it looks as if the current is coming out. So from north to south, you would have your current going into north to south. So here you would have a force acting down based on Fleming's left-hand rule. In the same way, at this side of the wire here, you have a force experienced up. So what you will find here is you would have an anti-clockwise rotation being experienced by your rectangular coil. And as I had mentioned, your split ring is basically going to rotate as the coil enters into this vertical position as a result of a 90-degree anti-clockwise rotation. So what happens here is that you will end up having this scenario, if you could kind of envision it with me, where your coil will now have your split rings being vertical. Now, eventually, the inertia of the coil is going to flip it. So you're going to have the coil now undergoing a total flip like this. Right? So the side here now becomes CD and the side here becomes AB. So because your connections are not changed, your electrical connections, you will find that the rotation of the coil continues in this manner. Okay? So in a nutshell, this is basically the consequence of having an interaction between the field around a magnet interacting with the field around a wire. Obviously, you have that force generated only being as a result of those interactions. If you take away the field, you will take away the force.